Hello. This lecture will cover pages 258 through 263 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 9D, Effective or RMS Values of both Voltage and Current. We're going to start out on page 258, and we're going to talk about this RMS. Another name for RMS is effective values of voltage and current. But before we do that, I want to refresh your memory that we had these equations here before that we said the true power or average power was equal to I squared R in watts. Now, that was true if I was a continuous value of current. It's DC. We said that it could be shown that the average power or the true power was equal to I max squared divided by 2 times R, where I max was the peak value of the AC waveform, and this was true for power in watts. We know that, and I'm using the current function here, voltage, it works the same way with this formula here, but the RMS, or the effective value of current, is tied to the maximum value by this equation. If you take I max, or the peak value of the current, and divide it by the square root of 2, we know that that's equal to 0.707 of I max, which is the effective value of that current. But all I'm doing is going up here in this formula, okay, and I'm putting in I max over the square root of 2 for the effective value. So keep in mind up here, you have to take a look at that. That's I max squared over 2. It's not I max over 2, the quantity squared. So I think you can see with the substitution up here that you can come down with this formula where the average power is equal to the true power, which is I max over the square root of 2 squared. It's just this formula using this as a substitution. So I come up with a third formula that I already gave you, that the average power or the true power is equal to the RMS value squared times R. That's for an AC circuit. So I'm comparing these two formulas here and here. Where this formula is effective, you take I squared R if I is DC, and down here it's the RMS, it's the equivalent. It's the effective value of the current if it's AC. It's not the peak if you're squaring it. So all three of these are formulas you can use, but I'm particularly interested in the first one, in this last one. So let's take a look here. We're going to relate powers here, and we're going to see how you come up with RMS values here. And this is for all waveforms. This is for all types of voltage waveforms. This is true. We have the average power is equal to I squared R in watts only if I is equal to I effective. We know that. So the power here, the average power, is equal to I effective squared times R. I'm going to call that equation 1. We also know that the average power, okay, is the power, instantaneous power, I squared R, over one period, 0 to t. That's the average divided by the period. So the average power, or the true power, if you have AC, okay, is equal to I squared R. It's that formula we had in the previous page. But it has to be, you take the average of that. So you integrate that from 0 to t, and take it times 1 over t to get the average value. All I'm going to do is equate these two waveforms to get a relationship between this I here, I effective, and this I instantaneous here, this time varying I. Well, if I equate those two equations, and they do this in the textbook, but I equate the two equations here. I take the square root of both sides, divide by R, and the R cancels, and I'm going to take a look at what we have. The relationship between any instantaneous value of voltage or current, we just did current here, don't forget. The effective value, the RMS value, is equal to the square root of that function squared and the average value of that. Let me say that in reverse order. It's the square of the waveform, average, or the mean, integrated from 0 to t, 1 over t, that function, squared, and then it's the square root of that. So RMS is square, mean, root in reverse order. So the effective value of a waveform is you take the square of the function, you take the average of the function, you take the square root. So that's true for voltage, current, and it's true for voltage. And we're going to use that. That goes for all waveforms. Now, continuing on, page 259, how is the RMS value related to the max value? Well, we know for a sinusoid, we could go right down to here, and we know that the RMS value of the current is equal to the max over the square root of 2, which is equal to 0.707 times I max, or we know the voltage RMS is equal to the peak or the maximum voltage divided by the square root of 2, which is equal to 0.707 times I max in volts. I mean, we know those, but we're going to, how did they come up with this? We're going to use a little bit of integral calculus here, and pretty easy to come up with this. We're going to let I, this is example 9.7 in the textbook, we're going to let I equal I max cosine of omega t. We know that the RMS value of I then is going to be this function squared. I just took this function and squared it. I found the mean or the average over one period, 0 to t, 1 over t. I took the square root of that. So using the trig identity where the cosine squared is equal to 1/2 plus 1/2 cosine of 2 phi, and knowing that the frequency is equal to 1 over t and the 2 pi over omega is equal to t, well, how did I come up with that? Well, I wrote it out here. You can see it. Omega is equal to 2 pi f. So we know omega is equal to 2 pi times 1 over t, because f is 1 over period. And I just solved this for t. So the period can be represented as 2 pi over omega. That's all. So all I'm going to do is use this trig identity up here, and I'm going to come down and I'm going to say that the RMS value of current, okay, and all you're working with in here is the maximum value, I max. But you see what you end up with is you end up with you bring out, the I max comes out in front here because it's a constant. The omega over 2 pi, that's the 1 over t. The 1 over t is a complex fraction. You flip it up to omega over 2 pi and you integrate over the period. 1/2 plus 1/2 the cosine of 2 omega t dt. Take the square root of that. Well, the cosine function over one period is 0. If you integrate that over one period and take the average of a cosine function, it's 0. So you just have the 1/2 here. So all I'm doing is integrating 1/2 dt from 0 to pi over omega. And when I do that and I evaluate it, you come down here and you end up with the omegas cancel. One of the 2's cancel, the pi's cancel, and you just have this inside this bracket, or you just have the square root of 1 over 2. So it's telling you that the RMS value of the current is simply equal to the maximum value divided by the square root of 2. This is the proof of using these equations down here. Just a little bit of integral calculus using a trig identity you learned in high school. So now you can just use these all the time. But the value of RMS being 0.707 of the maximum value of current or the voltage is only good for sinusoidal waveforms. This doesn't work for non-sinusoidal waveforms. Look what we started with up here. We assumed that the instantaneous current with respect to time was I max cosine of omega t, or sine omega t. It doesn't make any difference. We'd used a different identity. So these equations we get here, remember that. You can only take 0.707 of the maximum value to get an effective value or an RMS value if it's a sine wave. What about other waveforms besides a sine wave? How do we calculate their RMS values? Well, before I start, let me mention the fact that if you take a multimeter and you want to measure like the RMS value of this waveform here, or let's say you want to measure the RMS value of this waveform here, or let's say you want to measure the RMS value of a half-wave rectified signal where it looks like this and then it doesn't go here, it just goes to 0 for the second half of the period. Or let's say you have something exponential, you want to measure the RMS value of a waveform like this. Well, you need to have a true RMS meter to do that. You can't take any old voltmeter, because some voltmeters, when you put them on voltage or current and you measure that, it's assuming you have a sinusoidal waveform. Most of the more expensive pieces of equipment the multimeters are true RMS. Well, they'll give you a value for the true or effective value of that waveform, or the DC equivalent, if you will. But not all of them do that. You have to be careful. So, example 9.9 in the textbook I have here. Look at this waveform. The waveform is a linear function up to 1 second. It's from 1 to 2, it's 0, and then from 2 to 3, it's linear, but it's the negative slope. I want to find the average value of that waveform, and I want to find the RMS value of this waveform now. You can't use 0.707. So what I have to do, first of all, the average from over a period here, I defined what the period is here. The average of the period is 0 because the area above the curve and the area below the curve is the same. You take the average of that, you get 0. So that's the answer for the average voltage. But the RMS value here, you have to take a look, and you have to look at this function here. And you have to integrate this function. You have to square this function. First of all, find the linear equation between this point and this point. Then you want to square it, find the average value of it, and take the square root of it. And you have to add that. This is 0. And then you have to add that to this function. You have to find the linear equation for this function. You have to square it. Take the average from 2 to 3. And then take the square root of that. I did the math down here. Okay. The period comes out as a constant. I'm integrating from 0 to 1, the first function, 4t. I'm squaring it. That's the equation of that line, 4t plus 0. Remember your y equal mx plus b here? You have a point and you have a slope. You have to find the equation. And that's what I did right here. Here the equation's 0, so I put it in. What about the equation of this line here? Students have trouble with that. Well, you have a point, this point here, and you have a slope. Or you have this point here and a slope. You have to use what they call the point-slope formula to get the equation of that line because it has an intercept, a b-intercept up in here somewhere. I went ahead and did that. I found the equation of this line, and it's equal to a minus 4t plus 8. I square that, take the square root of it, integrate it between 2 and 3. I go through the integration, and I come up with the RMS value of 1.89 volts. That's the answer, 1.89 volts for the effective or RMS value of this waveform. You can't just take this 4 and square it up here. You can get 16 and find the area here, because you know integral calculus is nothing more than the area. And here you can't do it this way. Some students try to do it this way. The reason is because the square function is not linear. The squared function is not linear. You can't just square this 4 and get to 16 down here. It doesn't work. What about example 2? Here's a waveform. The period's defined from 0 to 8 seconds. I want to find the RMS value of that. Well, you can use integral calculus and you can find the RMS value, and I've done that. Get the equation of this line. Pretty easy. You get the equation of this line. There's your integral calculus to do it. You have to know how to do this on a final. You get 2.24 volts. But some students say, well, wait a second. That's linear when you square it, and this is linear when you square it. So just go ahead and square these waveforms. Take the average of them between their 0 and 4 and 4 and 8, and take the square root of it, and I did that down here. I didn't use integral calculus. I worked it this way, finding the areas. I get the same answer. Because when you square this waveform, it stays linear. What about example number 3 I have here? Half-wave rectified signal. This is called a half-wave rectified signal. Determine the RMS value of this waveform here, where t is defined as 2 seconds now. And it could have been 2 milliseconds. The dimension or the units of this axis has no effect whatsoever. If you take a look at the integration, the time has no effect on calculating these RMS values of current and voltage. In this case, we're finding Voltage. Previous examples, let's see. Yeah, we were finding voltage. Well, this could just as easily be current. This could be a peak current, don't forget. Well, just keep in mind as an identity, the sine squared, this is another identity we're going to use down here, but the sine squared is equal to 1/2 minus 1/2 cosine of 2 phi. So basically, here's what I'm going to start with. The RMS value of that waveform. I have to square the voltage. Well, the voltage is 20 times the sine of omega t. I look at this, I can pull that out. I don't care about the frequency. The peak is 20. So that waveform here, that sinusoidal waveform is 20 times the sine of omega t. I'm going to square it. But I'm only integrating it between 0 and 1. I'm only integrating it between 0 and 1. And then I have this. Don't forget that. You have to integrate 0 from 1 to 2. I use the trig identity up here, right at this point. Here's the cosine function. It goes to 0 over 1 complete cycle. So this whole term drops out. I have a simple integration here. End up with the square root of 200 over 2. Square root of 100 equals 10 volts. So here's a formula that most people just know. If it's a half-wave rectified signal, the equivalent RMS, or effective voltage, DC equivalent, if you will, of that waveform right there, if you had to replace it with a battery, is going to be equal to Vmax over 2. In this case, 10 volts. It's a nice thing to know. If that's 100 volts peak, 50 volt equivalent. No other way to figure that out other than this. You couldn't intuitively have seen that. Example number 4. Here we have a waveform, exponential. We've seen these in first order equations with these transient circuits. But anyhow, it's 5 minus 5e to the minus 2t, that waveform. That's the period, and it repeats itself. Repeats itself. Find the RMS value or effective value of this waveform here that has a peak of 5 volts. You can't use 0.707. So I take, there is the definition right there. There's the definition. That's the equation of that line. First step is I have to square that, and that's what I did. I squared it. Then I take the average of it. How do you take the average of it? You integrate it between 0 and 2, 1 over the period. Take the square root of it. I just worked through the math. Simple math. 3.98 volts is the answer. If I gave you that on an exam and I asked you what the effective value of that waveform is, there's no quick formula like there was in the halfway rectified signal. You have to work it out. It's 3.98 volts. The equivalent DC voltage of that circuit. And, you know, if you want a couple more practice problems to just understand this, you want to look at 911 and 912 in the textbook, and here they are. There's problem 911. The current waveform is shown, and that current is flowing through a 4 ohm resistor. Compute the average power delivered to the resistor. Okay. The average power flowing through a 4 ohm resistor is that. Okay. Let me say that again. That current flowing through that 4 ohm resistor is that waveform right there. I want you to compute the average power delivered to the resistor. So you have to calculate the RMS value of current of that waveform first. Square it and take it times the resistance. That's one of the equations. You can't use peak. That peak equation was only good for sinusoids. Hope you understand that. And there's another example with the answer. There's a current waveform that's flowing through a 10 ohm resistor. I want you to determine the average power. Okay. So you have to determine where the period is there. But you don't need in either one of these problems, you don't need integration. You can use the area. Calculate that way. But you have to get the effective value. First thing you have to get is the effective value of the current. Then you can go back and take the RMS value squared times that 10 ohm resistance. You should get the 80 watts that they have right there. In the textbooks, they give you a couple more examples like that. I mean, should you be able to do those two problems right there? Sure you should be able to do those two problems. But, I'll be happy if you can just, you get the general drift so you can do well on the exam when I give you this. So in summary, remember, you can only take that 0.707 times the peak value or the max value if it's a sinusoidal waveform. Every other waveforms, if you want to find effective value, and usually you want to find the effective value so you can calculate power. That's where you're going with that. The only way you can do it for non-sinusoidal waveforms is the techniques I've shown you here in these last 4, 5, 6 examples. And that concludes this lecture.